Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory undergraduate combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is exponential generating functions. So let's get started. And I'm going to start with a guiding example, an example that I will solve at the end, but to show you like what we're talking about. So let's say that Hn is the number of n-digit numbers with the following properties, that the digits are only 1, 4, and 7, and the number of ones is even. So you might want to stop the video and try to find out what Hn is. How many n-digit numbers are there whose digits are just 1, 4, and 7, and the number of ones is even? Okay, so again, in numbers, the order matters. So this is a question about permutations. We can reformulate that and say that we have infinite number of ones, infinite number of fours, and infinite number of sevens, a multiset where the repetition numbers of these three types of elements are infinite. And we have n1, which is the set of non-negative even integers, and n2, n4, and n7 are the set of non-negative integers altogether. And we want the number of n permutations of the multiset R. So we want to find n elements from R and permute them and find how many there are, but with the condition that the number of ones is in n1, the number of fours is in n4, the number of sevens is in n7. So we have these sets, n1, n4, and n7, that are informing us what the restrictions are for how many ones, how many fours, and how many sevens we can use. So this is how this is a very general kind of a construct. So you can pick your favorite set of non-negative integers and say that I want this item from my multiset to be chosen only this many times. And so another way of doing that is reformulating this is to talking about balls and boxes, as we usually do. This is also the same as placing n distinct balls into three distinct boxes. Those boxes are labeled, they're distinct. The labels are 1, 4, and 7, but with the restriction that the number of balls in box labeled I is an integer in ni again in those sets. So because we have n distinct balls, you can think of the balls as having a number on them. And if you put ball number 23 in a box, that means that you are selecting which one of 1, 4, and 7 is going to go in the 23rd place in your permutation. A distinct ball, when it goes in a box, not only is choosing that element from the multiset, but it's also assigning it a place in the permutation. And so whenever you have a n permutation of a multiset, you have a placement of distinct balls in distinct boxes, and vice versa. If you have a placement of distinct balls in distinct boxes, you have an n permutation of your multiset. And when we have this condition that says the number of balls in a certain box has to be from this set, then we are restricting them just like we were restricting those n permutations or the original problem, for example, that we had. So the point is that the most general problem that we want to talk about is we have a multiset and we have weird restrictions on how many of each of the elements we want to pick, and we want to make a permutation, an S permutation, an N permutation of them. So some easier cases of a similar problem would be if the original set wasn't a multiset, was just a set, and what you wanted was just the number of S permutations of a set with T elements. So this is also a multiset, but the repetition numbers are all 1. In this case, the answer would be T times T minus 1 all the way till T minus S plus 1, a falling factorial, a truncated factorial. You start with T and only go S terms. Why is that S terms? You don't go all the way to 1, you just go to S terms. Well, why is that? Well, because in your permutation, for the first spot, you have T choices. For the second spot, you can't use that guy that you just used. You have T minus 1 choices. And since you have S spots, you get this falling factorial. So that was a simple case one we had done before. Another case would be if we just have as much choices as we want from any one of the elements. So we have a multiset, but the repetition numbers are truly infinite in the sense that we can use as many of any elements as we want. In that case, to find the number of S permutations, well, you have T choices for the first spot, you have T choices for the second spot, you have T choices for the next spot. So this T to the S, because you're never going to run out. And since you're writing a permutation, you could, for example, pick U1 at will all the time, or any one of them for your permutation. Again, this would be an easy case where we know the answer. There's yet another case where we have in previous videos talked about finding S permutations of multisets. That's if you have N1 of V1, N2 of V2, and T of Vt. So we have T items again, and the repetition numbers are N1, N2 through Nt, but this time N is the sum of these numbers, and we want the number of N permutations. So we're permuting everything. We're not leaving anything on the board. We're permuting all the elements that we have, and the answer to that is a multinomial coefficients. N choose N1, N2, Nt, and the formula for that is N factorial divided by N1 factorial, N2 factorial, all the way till Nt factorial. And the way to do that is to, we have seen this in previous videos, you first pick in your N permutations, where are the V1s going to go? Well, there's N1 of them, and you have N choices, so that's N choose N1. For V2s, now you have N minus N1 choices, places to pick from, because you have already filled in N1 of the choices, and you have to pick N2 of them. So it's N minus N1, choose N2, and you have to multiply those two. And you have to keep multiplying these binomial coefficients. If you actually write down the formula for that, you see a lot of things cancel, and you're left with this multinomial coefficient. But those are the easier cases. So now we are going to do this using generating functions. This very general case. These other cases, the easier cases, we didn't use generating functions, but for the case we want, where the restrictions on the elements of each type could be that the number of things we want from this is even, or it's from 0 to 8, or anything like that, then we are going to use generating functions. But we're not going to use the same the kind of generating functions that we used previously, for example, in finding S combinations of a multiset, but we're going to use exponential generating functions. We had defined the ordinary generating function of a sequence, and we've used it to find the number of S combinations of multisets. But and we also use that to solve recurrence relations. There's actually a lot of different kinds of generating functions. For example, there are generating functions of two variables that are used for the set of numbers that have two variables. For example, Stirling numbers of the second kind. There's an N and a K, and so you might want to look for generating functions of two variables to be helpful with them. And for different purposes, different kinds of generating functions are useful. And each one of them has its own application. Here we use exponential generating functions, and these guys are useful when you want to do S permutations of a multiset, and therefore tailor-made for what we want to do here. So I'm going to tell you what that is. So given a sequence H0 to Hn, the ordinary power series for it was we just used these as coefficients of x, the constant term, the coefficient of x squared, and so forth. And this was the ordinary generating function, and we wrote that that G is, if G was sort of the closed form of this thing, is the ordinary power series for Hn. So that's how we had defined those before. But given the same kind of a sequence, we can define a different kind of a generating function called the exponential generating function of that. And we often use, or at least I use capital letters, capital G of x. And the difference between this and the ordinary one is that I don't just put the H1, H2, and Hn as coefficients of powers of x, but first I divide them by factorial and do that. So I put H0 over z factorial plus H1 over 1 factorial x plus H2 over 2 factorial x squared, and all the way till a typical term being Hn over n factorial xn. And this guy is going to be written as EGF, the exponential generating function of this sequence. So the same sequence, you could make the ordinary power series for it, or you could make the exponential generating function. Again, the proof of the pudding is the eating. You would do the second one if it was of any use, and we will see that this is the one that's going to be useful in finding S permutations of a multiset. And EGF, again, stands for exponential generating function. Now, I should say a little bit for this. If G is the ordinary power series of a sequence, then you know that Hn is the coefficient of xn in the Taylor series expansion of G at x equals 0. Not so with exponential generating function. There's a for exponential generating function, your original sequence is not the coefficient of xn, because you divided it by n factorial, and that became the coefficient of xn. So G, a function, then the Taylor series. So if you have just a general function, then its Taylor series expansion is like this. And in some sense, the exponential generating function is more natural, because if g is the exponential generating function of hn, then g of x is also h0 plus h1x plus h2 over 2 factorial x squared and hn over n factorial xn. So just like when we took derivatives and we wanted to find the Taylor series, we had to divide by n factorial. Here we are doing the same thing with hn. And so hn really is not the coefficient of xn, but it's the nth derivative of the function at 0. When we find Taylor's series, the coefficient of xn is the nth derivative at 0 divided by n factorial, and here our hn is just that derivative. We are manually ourselves dividing it by n factorial. And so if we want to get this hn back from the coefficient of xn and not the derivative, then we have to multiply it by n factorial. So if someone tells you, here's an exponential generating function, and I'm going to tell you what the coefficient of xn is. Now get back your original sequence. You have to multiply that coefficient of x to the n by n factorial, because to get to create the exponential generating function, you first divided it by n factorial. On the other hand, if they just tell you, here's a function, here's the nth derivative at 0, then they've given you already the hn, and you don't have to divide it by n factorial to get it. So again, you start with a sequence and you make an exponential generating function. If someone gives you not the exponential generating function, but the coefficient of xn in the power series expansion of gx at x equals 0, then to get your sequence back, you have to multiply by n factorial. Okay, so now let's look at some examples. So the exponential generating function of all ones, what is that? In the case of ordinary generating functions, we saw 1 plus x squared plus x cubed and so on was 1 over 1 minus x, and that ended up being really important. In this case, it's going to be 1 plus x squared over 2 factorial plus x3 over 3 factorial and so on. And if you remember your calculus, this is the expansion of e to the x. This is the power series of e to the x. So the closed form for that is e to the x. So e to the x is the exponential generating function for the sequence of all ones. In fact, this is why this might be called the exponential generating function. Now, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. What's e to the apple? Well, it's 1 plus apple squared over 2 factorial plus apple cubed over 3 factorial. So if I plug in ax for x, I get e to the ax is 1 plus ax plus a squared over x squared over 2 factorial and so on. And this means that e to the ax is the exponential generating function of a to the n. So if you want the exponential generating function of 3 to the n, for example, it's going to be e to the 3x. Now, what about falling factorials? This is another example. So this is a sequence of falling factorials. Again, remind yourself that the falling factorial is a truncated factorial. You start with n and you act like you're writing a factorial, but you stop. You stopped after k factors, and that's called a falling factorial. And it's the same as saying that you have n factorial, but you divide it by n minus k factorial to get rid of the extra terms. And what's the exponential generating function of that? Let's call it g of x. So g of x then, by definition, is going to be all of these falling factorials, but at every one of them we divide by n factorial and multiply by x to the n. Now, when we do that, if you use the fact that n falling factorial k is n factorial over n minus k factorial, this is what we get. And these are now just binomial coefficients. And so we get n choose 0 plus n choose 1 times x plus n choose 2 times x squared and so forth. And by the binomial theorem, this is 1 plus x to the n. So 1 plus x to the n is the exponential generating function of falling factorials. Now remember that 1 plus x and x to the n, that same function was the ordinary power series of the binomial coefficients, but it's the exponential generating function of the falling factorials. Now, when we used ordinary generating functions, we saw that multiplying them was useful. So the question is that what happens when you multiply exponential generating functions? And this is the key for their usefulness for finding S combinations of permutations. So let's say that I have f1, that's an exponential generating function of some sequence of numbers. I'm calling it the sequence an going from 0 to infinity, but because I'm going to have a lot of generating functions, I'm going to put a superscript of 1 to show that this is the sequence for this f1. And then f2 is going to be for another sequence, and these are all exponential generating functions. And I want to know what happens when I multiply them. When I multiply them, well, I will get something, and that will be the exponential generating function of some sequence, but what sequence? So what is that Cn? So now, when we say that f1 is the exponential generating function of that sequence, then that it means that f1 equals that. And again, just like ordinary power series, we don't actually mean equal in the sense that this power series converges to f1. We just mean that f1 is holding the information for us for what these terms are. This f1 will definitely converge for x equals 0 and presumably for some other x. And we're not really interested in convergence. We're just interested in for the fact that f1 we can retrieve our sequence from f1, and the same with f2, and so on with the ft. Now, so Cn is going to be the coefficient of, it's not going to be coefficient Cn is going to be n factorial times the coefficient of x to the n in f1 through ft. f1 through ft, when multiplied, is the exponential generating function for Cn, but if someone gives you the coefficient of x to the n in f1 through ft, you have to multiply it by n factorial to get Cn, and we're about to do that. So f1 is this guy, f2 is that guy, and ft is that. And the question is that what's the coefficient of x to the n in the product? After I do that, I multiply it by n factorial, and I will get my Cn. So how am I going to get x to the n when I multiply these? Well, I've got to take one term from the first one term from the second one term from the last one, and one term from all the ones in the middle, and get x to the n. So I will get something like this as the coefficient of that x to the n. But if I want to get x to the n, it has to be that these S1 and S2 through STs all add up to n. Otherwise, I won't get x to the n. I'll get x to something else. Because to get x to the n, all the exponents have to add up to n. So S1 plus S2 plus ST has to be add up to n, and they have to be non-negative numbers. And these are the coefficients that I have. So I will get something like that. And I will get one of these every time I have S1 and S2 and ST all the way to ST that add up to n. So I will get, when I combine them, when I combine like terms, I will get a sum of terms like that. And then Cn is going to be n factorial times that. And if you multiply this by n factorial, you bring n factorial in here, you get exactly n factorial divided by S1 factorial, S2 factorial, ST factorial. And so you get a multinomial coefficient. So this is going to be my Cn. So let me recap that. So if you have a bunch of exponential generating functions of some known sequences, then the product is going to be the exponential generating function of this messy sequence. But this messy sequence is a sum of terms, and each one of them has a multinomial coefficient. But we're going to be interested in one particular case where these a's are, with these original coefficients were all ones. But to do that, we will talk about indicator generating functions. We had done this for ordinary generating functions in the previous video. Now we're going to talk about exponential generating functions. So let's say someone gives you a set of positive integers, non-negative integers, and what you do then you make this generating function, this exponential generating function, but it's not of this. I mean, you can't have an exponential generating function of a set. It's not of the sequence. But the way you make this is you only keep the terms where the exponents come from that set, and this thing is called the exponential indicating generating function of that set. So if there's a 3 in here, you'll have a x cubed over 3 factorial. If there's a 47, you will have an x 47 over 47 factorial. If there's not a 23, then you will not have an x to the 23 term. So you can turn this into an exponential generating function if you want of a set that consists of a whole bunch of ones and zeros. But I don't want to do that at this point. So for example, here's a set of even integers, even non-negative integers. What is the exponential indicator generating function of that? So by definition, you just keep the powers that you have in your set. So you have x to the 0, x squared, x to the 4th, x to the 2k, but you divide them by the appropriate factorials. Okay, does this have a closed form? So we start with e to the x. We often do that, just like with ordinary power series, we often start with 1 over 1 minus x. With exponential ones, we often start with e to the x. E to the x has this expansion 1 plus x over 1 factorial and so on. And that's sort of like the one we want, but this one does not have the odd power. So how do we get rid of that? The trick we use is that we find e to the minus x. E to the minus x, that means instead of x, I put minus x, and what happens is that every odd term will have a negative in front of it. And then if I add these two, those odd terms will go away, but I'll have twice the even terms, and so I divide it by 1/2, and then I will get what I wanted to. So the exponential indicating generating function for even integers, even non-negative integers, is e to the x plus e to the minus x divided by 2. Okay, now we go back to our guiding example. Let me remind you what it was. It was the number of n-digit numbers with digits 1, 4, and 7, such that the number of ones is even. So the reformulation was that n1 is the set of non-negative even integers, and 4 and 7 are set of non-negative integers, and we want n permutations of the multiset R, such that the number of ones is in n1, the number of fours is in n4, the number of sevens is in n7. And we said that that's the same as placing n distinct balls into three distinct boxes labeled 1, 4, and 7, but with the box in labeled I getting the number of balls in that box being an integer in the set ni. So that's the thing that we wanted to do. Now these going from n permutations of a multiset to placing balls in boxes is something that we have now already discussed. We now want to introduce exponential generating functions into that. So let's talk about that. So if we have R, which is a multiset with t types of elements and multiplicity of infinity for all of them, repetition number infinity for each element, and we have these sets of non-negative integers. Each one of them is going to put a restriction on how many of each one of those elements are we going to take in our permutations. And we're going to find the indicator generating function, but not just the indicator ordinary power series, but the exponential indicator generating function of each of these sets. This is going to be the new twist that we're going to add in. So now, then the following three numbers are equal. Now, some of this we've seen before. The last thing I'm going to say we have not seen before. So number of placing s distinct balls into t distinct boxes, such that the number of balls in the ith box is an integer in this set n. Again, go back to the guiding example. Those sets n1 through n2, one of them could be like even integers, another one could be between 1 and 8, another one could be all in positive integers, and so forth. So this number is the same as the number of s permutations of the multiset R, such that the number of vi's used is an integer in ni. And again, I've talked about just very recently in this video, I've talked about why these two things are the same. So that's not a surprise. This number is the same as also this sum of multinomials. Now, this sum of multinomials needs a little bit of explanation. And so let me do that in the context of finding s permutations of the multiset R with these restrictions. So if I want to do that, one way to do that is to say, well, let me pick the s elements first, and then I will permute them. If I pick the s elements, then I have to know how many v1s I want, how many v2s I want, how many vt's I want. So I want to solve m1 plus m2 plus mt equals s. I want to know m1 is going to tell me how many v1s I use, m2 is going to tell me how many v2s I'm going to, and so on. But I've got to have the condition that mi is in ni. So m1 is in n1, m2 is in n2, and so forth. So given that, if I solve that and I find those, then I know how many v1s, v2s, and vt's I want. Then I'm back to one of the easier cases where I have a whole bunch of things and I want to permute all of them. And we saw that the answer to that is a multinomial coefficient. But that if I solve that once, I just got one possibility. I have to solve this again because there might be multiple. In fact, there will be plenty of solutions to this equation. And for each one of them, I will have one choice of how many v1s, how many v2s, how many vt's to take. And for each one of those choices, I will have a multinomial coefficient ways of doing it. And so then when I add it up, I will get the answer that I want. So I just proved to you that this the sum of multinomials is the same as those other two formulations of numbers. But what I'm going to say next, which is something that I'm not going to prove in this slide, but on the next slide, is that this sequence HS, its exponential generating function is the product of those exponential indicating generating functions of Ni. So if you take these exponential indicating generating functions, multiply them, you will get the exponential generating function for this sequence of numbers that we want. And so this is our clue to how we're going to solve our S permutations of multisets when the restrictions are weird, is that we will write down the restrictions in terms of exponential indicator generating functions, we find the product, and then we try to retrieve the answer from that, or glean some information from that if we can't find the final answer. So let's just look at why this last thing is true. So we have so what's the setup? We have a bunch of sets. These are sets of non-negative integers, and we have the exponential indicating generating function for each of them, and we have that HS is the sequence the product of these exponential indicating generating functions is the exponential generating function for some sequence, and that sequence is the sequence HS. And we want to know what this HS is. What we want to show is that HS is this sum of multinomials, which is the answer to the question of S permutations of a multiset with weird restrictions on each one of the types. So that's what we want to show. Now, we did look at what happens when you find the product of any exponential generating functions, and we got this product that had multinomial coefficients but also had these things. But in our case, our x1 through xt's are exponential indicator generating functions. That means that the coefficients are either 1 or 0. They're 1 if xi is ni, and 0 if xi is not ni. So when one of these coefficients is 0, well, of course, there's going to be no contribution to what we get. But so the only time we're going to get a contribution is all of them are 1, and all of them are 1 if x1 is in if x1 is in n1, x2 is in n2, x3 is in n3, and so forth. And it has to be also true that x1 plus x2 plus x3 equals s. So the only way we're going to get 1 is if x1 is in n1, xt is nt, and all of those guys add up to s, and that's exactly what this is. So in that case, these a's become just 1, and we are left exactly with that condition. So we are left with m1 plus m2 equals s, and each one of them is an element of ni. That's the condition we need to make these to be 1. So we have now proved it, and we're now ready to do our guiding problem. But before that, I want to tell you about a special case. Special case where I don't have to think about exponential indicator functions is the following: is if I have a multiset where I have n1 v1s, n2 v2s, and nt vts, and each one of these is allowed to be infinity, and I just want the number of s permutations of R, and so the restrictions here are not weird as they were before, but they're just that v1 I only can take 0, 1 through n1, v2 I can take 0 of it, 1 of it, 2 of it, or n2 of it, or anything in between, and so forth. So I just have a range of numbers that I can take for each one of the elements. In that case, then gx still will be a product of exponential indicating functions, except those will just be either e to the x if the repetition number is infinite, or it will be a truncated power series for e to the x, a partial sum of the power series for e to the x if ni is less than infinite. So in this case, those terms that you have to multiply are a little bit simpler. So now let's go back to our original problem. We want to find the number of n-digit numbers with digits 1, 4, and 7, with the condition the number of ones is even. And so h0 is 1, because if you want a 0-digit number, can you find a 0-digit number? Can you construct a 0-digit number with digits 1, 4, and 7 such that the number of ones is even? Will you not be able to do that? And the answer is that there's no reason you can't do that. You actually don't have to do anything. You've already done it. And so there's only one way to do that. You can take that as a part of the definition if you want. And H1 is 2 because the only things you can do is either take a 4 or a 7, because you can't use any ones, because you have the number of ones has to be 0. That's the only even integer that's allowed. For n equals 2, H2 is 5, because the possibilities are more. You can have 11, that's 2 ones, or 47, 74, 44, or 77. Already H3 becomes a little bit more too complicated to want to do. But the way we are going to do it, we're going to say that we're going to find the exponential generating function for this sequence, as opposed to finding it. So what is that? That's going to be a product of exponential indicator generating functions for the sets that give us the restrictions. For 4 and 7, I don't have any restrictions, so I can have 1 plus x squared over 2 factorial and so on. For 7, the same thing. For 1, though, for the ones, I only have the even terms. So that's the the exponential indicator generating function. Why am I using exponential ones? Because those are the ones that when you multiply, you get those multinomials, and we've proved that you get the number of S permutations. If you wanted the number of S combinations, then you would not use exponential generating functions, but you would use ordinary power series. But now what can we do with that? But that first one is e to the x plus e to the minus x over 2. We already saw that. The other two are just e to the x's. This is e to the 2x. You can multiply through, and you will get 1/2 e to the 3x plus e to the x. And we know that e to the x is the exponential generating function for 1, and e to the 3x is the exponential generating function for 3n, and here we're adding them. So when you add them, you just get the sum, and then you have to divide by 1/2. So now we have actually a formula for hn. It's 3 to the n plus 1 over 2. It's magic if you ask me. And so we could check. If you put 0 here, you get 1 plus 1, 2 divided by 2, you get 1. If you put 1, you get 3 plus 1, which is 4 divided by 2 is 2. If you put 2, you get 9 plus 1, which is 10 divided by 2, and that's 5. If you put 3, you get 27 plus 1 is 28, divided by 2 is 14. So, and we now found a formula. This is the end of this lecture on exponential generating function. There's a whole bunch of videos on generating functions. There's one further one that I yet have to make about partitions of an integer, but you can watch any of those if you want more on generating functions. In fact, you should probably watch some of those before you have watched this one. This is the end of this video. If you liked it, if you like this video, please like it. And if you want YouTube to subject you to more videos like this, please subscribe to my channel. I will see you in the next lecture.